Now that we've talked about precipitation reactions, we need to think some about what's really happening and what part's really changing when we do a reaction. To do this, we're going to use this example balanced chemical equation of a precipitation reaction. If you take potassium hydroxide and you mix it with magnesium nitrate, which are both aqueous, you get a solid that forms called magnesium hydroxide, and that's the reason it's a precipitation reaction, is because you have this solid that forms at the end. Now, in terms of what's actually happening of the chemistry, it's only the magnesium hydroxide is the only thing that's really changing. So remember that when it's aqueous, what that means is that there are K plus ions, hydroxide ions, magnesium ions, and nitrate ions. And some of them there are two of, and some of them are one of per molecule. But the idea is all four of these are present in solution. When you mix these together, you still have, I lost my pen. There we go. Potassium ions and nitrate ions floating around. Whereas the magnesium and hydroxide are no longer floating around, they formed a solid. So in terms of the chemistry that's really happening, it's the magnesium and the hydroxide ions that are connecting and reacting. The potassium and the nitrate, while they're there, they're not doing anything. Nothing has changed about the potassium and nitrate in this reaction. As reactants, they were aqueous ions floating around. As products, they were also aqueous ions floating around. Nothing changed. So, how do we represent this? What's another way we can write this reaction? So I'll start by saying this first reaction here is perfectly fine. This is the balanced chemical equation. It works, and in a lot of instances, it's perfectly fine. It tells us, for example, if we want to look for certain concentrations of these different solutions to make some magnesium hydroxide, what amounts we would need of each to make, let's say, 10 grams. We can figure that out, go do the problem we solved last video, but sometimes we want to better focus on what's really occurring and what chemistry is happening. To do this, we use two ideas. And the first one really is mostly a way to get to the second idea. So the first idea is something called a complete ionic equation. So the idea of a complete ionic equation is these aqueous symbols can be convenient for talking at these, but it doesn't give a good picture of what's really happening. So for a complete ionic equation, you take every aqueous ionic molecule we got here, and we break it apart. So if it's something that's aqueous, and while being aqueous, it's ionic, so in some way it can break into separate parts, whether they be polyatomic ions or just single atoms that easily become ions like potassium or magnesium here. So we break everything apart that is an ion. So for example, in this case, we would have 2 K plus aqueous plus 2 hydroxides that are aqueous plus 1 magnesium 2 plus that is aqueous plus 2 nitrates that are aqueous. Now note here, I did write this is 2 nitrates rather than NO3 with this 2 down here because nitrates are polyatomic, so it sticks together, but nothing suggests that both nitrates should stick to each other. The idea behind this compound is that there were 2 separate nitrates that each react connected to this one magnesium because it balanced out the charge. But if we're breaking everything apart, those nitrates have no particular reason to stay together, so we talk about them as 2 separate nitrate ions. But we don't break them apart into single nitrogen and 3 separate oxygens, because as a polyatomic, they all function together, all 4 of those atoms, as like a single ion, like Cl-. Good. So those are our reactants. We then draw a reaction arrow, and it makes our products, and our products are going to be K plus is still an aqueous ion. Plus now we have 2 nitrates. And our magnesium hydroxide, we just write as one thing because it's a solid, so it doesn't break apart. So this equation here would be our complete ionic equation. This is a picture of what was in the reactant and what was in the product side, where we recognize that things that say AQ, if they're ionic, break apart. They don't stay together. So you don't have K plus and OH minus floating around in water together. They've split up, and the K plus and the OH minus don't have to be necessarily directly next to each other. Because they're breaking apart in water, they're actually likely to be surrounded by water molecules instead. They're solvated. So they're going to be surrounded by that. Whereas the magnesium hydroxide will fall to the bottom like a rock because, well, it is a solid and it'll do that, and it won't break apart into anything because of that. Now, this still doesn't get at the question of what's the chemistry happening, because right now we have something we call spectator ions. Spectator ions are going to be ions that don't do anything, that don't participate in the reaction. I don't want to say don't do anything at all, but they don't participate. So that means they're the same on the reactant and the product side. So if we want a picture of what things are actually reacting and what things are just kind of sitting around like, hey, they're here, they're like spectators, they're watching the reaction occur, but they're not doing anything, we have another type of reaction equation we call a net ionic equation. So in our net ionic equation, we remove the spectators. So the way to identify a spectator is if you compare in the complete ionic equation where it occurs in the reactants and where it occurs in the products. If there are no changes, then it's a spectator. And by changes, we mean is it connected to some new atom, did a phase change or something like that. So for example, this potassium here and this potassium here are both aqueous in the same number. They are spectators. So for coming up with my net ionic equation, I'm going to mark them out. Note, if you have to turn in the complete ionic equation, please turn it in without all the markings on it. But this is a good way to write it up to get a net ionic. So you've got your K pluses, those go away. Now the next thing I go to is this hydroxide here. Well, now it's connected to magnesium, it's a solid, so it's not a spectator. I can't get rid of the hydroxide. Same with this magnesium on the reactant side. It changes because it becomes a solid. This nitrate, though, is exactly the same as this nitrate. Those are both spectators. For writing my net ionic, I can treat it like it's not there. So what really occurs in this reaction, I keep losing my marker, there we go, is that magnesium 2+, aqueous, and 2 hydroxide ions, aqueous, are reacting to form 1 magnesium hydroxide. That doesn't look like an H correctly. I did not mean to put an extra letter there. We'll just rewrite that. Yeah, it's faster than trying to find the little eraser thing. So magnesium, OH, 2, solid. So this, minus my little boo-boo where I wrote like a little extra term, is the net ionic equation. So when you mix these two compounds together, the reaction you're getting is that magnesium plus 2 hydroxides would make magnesium hydroxide. So that's what we would get. Now, you can also do this with something that wasn't necessarily a precipitation reaction. So let's take a look at one other. So let's say you had KOH plus HBr. And these are both aqueous. And they react to form water, liquid, plus KBr, aqueous. Now, we'll talk about how to make a prediction for a reaction like this in next week's videos. But for right now, I'm just telling you this is a reaction that can occur where KBr is aqueous and water is a liquid because water doesn't, we're going to say the water primarily doesn't break apart in itself. Note, in 1212, we'll discuss this in some details. A very small number of the water molecules will break apart into separate ions, but for the most part, most of the water stays together. So that's what we're dealing with here. So here I can also do a complete and a net ionic. However, since you just saw an example, I want you to pause here and give it a try first on your own, and then go over and see if your answer matches up with mine. Go away. Not you, the taskbar. I want you to stay. Please don't leave my video. Please actually finish. Okay. Hopefully you paused me at some point during that little piece and you actually did this. So let's come up with our complete and our net ionic. To do this, first we need to see what it breaks apart into. So we have K plus aqueous plus hydroxide aqueous plus H plus aqueous plus Br minus aqueous. So no polyatomics in this one to worry about. Reacts to form water. Doesn't have an AQ next to it, has an L, so we're not breaking it apart. Just like you also won't break apart gases if you see any in your problem. And then we have K plus aqueous plus Br minus aqueous. I almost had enough room, but not quite. So this would be our complete ionic equation. So if your problem just said, hey, write the complete ionic, you'd be done there. Note, in case you're trying to do an online homework program of some type, make sure you put the charges in the right place. Make sure you get the phases on things. Forgetting phases is a very common way to mess up with these, and not relevant for this one, but do make sure your equation is balanced. And okay, it's not that it's not relevant here. This reaction is just already balanced, even with just ones in front. But make sure you balance it. If it doesn't show up as balanced, that can cause some of your problems too. Now, let's say on the other hand, instead ask for a net ionic, or ask for both. So for the net ionic, we want to get rid of things that occur on both sides. So K plus and K plus can go away, Br minus and Br minus can go away. So this reaction is that H plus aqueous plus OH minus aqueous reacts to form water. And so actually, this we'll get into next week's topic, is this is the reaction that is an acid plus a base. And we'll talk about how we know that next week, but for right now, you don't have to worry about that part. But you'll be getting it shortly. So, the other thing to notice, one other thing I just noticed that I do, to let you know, you may notice I sometimes do some reordering. This is because in general, when we write out our net ionic, we tend to put the cation plus the anion. However, you would be perfectly fine if you wrote OH minus aqueous plus H plus aqueous reacts to form water. That's perfectly fine. And that would actually match up with the order you have it written in the complete ionic if you go up there. It's just my brain sort of automatically tells me, oh, right, I tend to put the cation. I put the cation first here, so I do H plus plus OH minus. The bottom is also correct. It's the only reason for the reordering. It's not something more complicated than that. And sort of over time, as you stick with chemistry or whatever science you end up going into, you learn there are trends that tend to be true within this. And sometimes, depending, is that it may be that that's a rule that has to be followed, or it could be that, well, that's just the way we do it, but technically the other thing is still okay too. So that finishes what we have to do about complete and net ionic equations. We use those to better represent what's happening in the reaction. Similar here to what we had in the last one. It's actually the H plus and the OH minus reacting to form water. The K plus and the Br minus are present, but they don't do anything in this particular reaction. They're spectator ions. They don't participate. So really, if we want to know the chemistry, the net ionic focuses on what's really happening. But the complete ionic and the balanced chemical equation at the top are both helpful because I don't have a bottle of just H plus here. Like I don't just pull a bottle of H plus off. It has to be attached to something. So in this case, I used HBr as my source of H plus. And that'll come up in other cases too, where you have two ions you want to react. Well, then you've got to go figure out something that would have that ion in an aqueous solution so I can get it to react with the other ion. So sometimes it's just a case of, well, I want some chlorine because I want to react with this silver to form silver chloride. So I need to go find something that's got chlorine in it that will dissolve in water that's aqueous to then react with the silver in my solution. So in that case, yes, you need the fact that it's, maybe you got your silver from silver nitrate. So you needed that silver nitrate, even though the nitrate doesn't participate in the reaction, because you needed a way to get the silver into solution. And then later on, you also want to get the chlorine. Maybe you just use salt water, use sodium chloride, but maybe you use something else. But you need a source of those ions to then make that solid, whether it be silver chloride, the example we looked at earlier of magnesium hydroxide, or here you just wanted to do an acid-base reaction, which ends up making water. So you still need a source for those. That's why we don't just give the net ionic and say ignore all the other stuff, because depending on what you're doing, different equations will actually be the ones that are most useful to you.